In the annals of scientific discovery, few theories have revolutionized our understanding of the universe as profoundly as Albert Einstein's general relativity. Published in 1915, this groundbreaking theory transcended the boundaries of classical physics, offering a radical new perspective on gravity, space, and time. It wasn't merely an incremental advancement, it was a paradigm shift that shattered long-held assumptions and unveiled a cosmos far more intricate and awe-inspiring than previously imagined. Before Einstein, gravity was understood through the lens of Isaac Newton's law of universal gravitation. This law described gravity as a force acting instantaneously across vast distances, holding celestial objects in their cosmic dance. While remarkably successful in explaining the motion of planets, Newton's theory left some fundamental questions unanswered. What exactly was the nature of this mysterious force? How did it traverse the vast emptiness of space? Einstein's quest to unravel these mysteries would lead him down a path of intellectual exploration, culminating in one of the most elegant and profound theories in the history of science. General relativity, at its core, is a theory of gravitation. Unlike Newton's concept of a force acting at a distance, Einstein proposed that gravity arises from the curvature of a unified fabric, space-time. Imagine, if you will, a trampoline as a two-dimensional representation of this fabric. Placing a bowling ball at the center of the trampoline causes it to sag, creating a curvature around the massive object. This, in essence, is how Einstein envisioned gravity. Massive objects like stars and planets warp the fabric of space-time around them, and it's this curvature that dictates how objects move within this cosmic tapestry. In the words of physicist John Wheeler, matter tells space-time how to curve, and curved space-time tells matter how to move. To truly grasp the elegance of general relativity, we must first abandon our intuitive understanding of space and time as separate entities. In the Newtonian worldview, space was an unchanging backdrop, a cosmic stage upon which the drama of the universe unfolded. Time, similarly, was considered absolute and immutable, ticking away uniformly throughout the cosmos. Einstein, however, shattered this illusion of separation, demonstrating that space and time are inextricably linked, woven together into a seamless, four-dimensional fabric, space-time. Imagine space-time as a vast, flexible sheet. This sheet represents the combined essence of space and time, a unified entity that permeates the universe. In the absence of any matter or energy, this fabric would remain flat and taut, like a perfectly stretched canvas. However, the presence of mass and energy warps this fabric, creating curves and indentations. Think of placing a heavy ball on a stretched rubber sheet. The sheet sags under the weight of the ball, creating a depression. Similarly, massive objects like stars and planets create distortions in the fabric of space-time. This curvature is what we perceive as gravity. Just as a marble rolling on the stretched sheet would be deflected by the depression created by the heavy ball, objects moving through space-time are guided along the curves created by the presence of mass and energy. In this sense, gravity is not a force acting at a distance, but rather a manifestation of the geometry of space-time itself. Einstein's revolutionary insight was that gravity is not a force in the conventional sense, but rather a consequence of the curvature of space-time. This curvature arises from the presence of mass and energy. Imagine a bowling ball placed on a trampoline. The bowling ball represents a massive object, such as a star or a planet. The trampoline represents the fabric of space-time. The weight of the bowling ball causes the trampoline to sag, creating a depression around it. This depression represents the curvature of space-time caused by the massive object. Now, imagine rolling a marble across the trampoline. If the marble rolls near the bowling ball, its path will be deflected by the curvature of the trampoline. This is analogous to how gravity works in general relativity. Objects with mass curve the space-time around them, and other objects moving nearby follow curved paths due to this curvature. The more massive the object, the greater the curvature it creates in space-time, and the stronger its gravitational influence. This curvature of space-time is not just a theoretical concept, it has been experimentally verified. One of the most famous confirmations of general relativity was the observation of the bending of starlight during a solar eclipse in 1919. Before delving further into the depths of general relativity, it's essential to understand its foundational pillar, special relativity. Published by Einstein in 1905, this theory revolutionized our understanding of space, time, and motion, setting the stage for his later masterpiece. At the heart of special relativity lies a deceptively simple, yet profound postulate. The speed of light in a vacuum is constant for all observers, regardless of their relative motion. This might seem counterintuitive at first. Imagine chasing after a beam of light. You might expect that as you move faster and faster, the speed of light relative to you would decrease. However, special relativity tells us that this is not the case. No matter how fast you move, even approaching the speed of light itself, the light beam will always appear to be moving away from you at the same constant speed. This constancy of the speed of light has profound implications for our understanding of space and time. To accommodate this universal speed limit, Einstein realized that space and time could no longer be considered absolute and unchanging. Instead, they must be relative, their measurement dependent on the observer's motion. Section 5. Time warps, dilation, and its real-world effects. One of the most mind-bending consequences of special relativity is time dilation, the concept that time is not absolute but rather stretches and contracts depending on relative motion. Imagine two identical clocks, one stationary on Earth and the other traveling at a significant fraction of the speed of light. According to special relativity, the clock in motion will tick slower than the stationary clock. This difference in timekeeping is not an illusion or a mechanical malfunction. It's a fundamental consequence of the nature of space-time. As an object approaches the speed of light, time itself slows down for that object relative to a stationary observer. This phenomenon, while seemingly bizarre, has been experimentally verified countless times, and it's not just a theoretical curiosity. Time dilation has real-world implications, particularly in the realm of satellite technology. GPS satellites, orbiting Earth at high speeds, experience time dilation due to their motion and the weaker gravitational field at their altitude. To ensure the accuracy of GPS systems, engineers must account for these relativistic effects, making minute adjustments to the satellite's clocks to compensate for the time dilation they experience. Without these corrections, our GPS systems would quickly become inaccurate, highlighting the tangible impact of Einstein's theories on our everyday lives. As the 20th century progressed, numerous experiments began to confirm the predictions made by Einstein's theory of general relativity. One of the most famous confirmations came in 1919, when Sir Arthur Eddington observed a solar eclipse. This observation provided the first empirical evidence that light bends around massive objects, just as Einstein had predicted. Over the years, further experiments and observations continued to support the theory, solidifying its place as a cornerstone of modern physics. The 1910s and 20s were a period of remarkable transformation in the world of physics. Einstein's theories challenged and ultimately reshaped our understanding of space, time, and gravity. This decade of revolution not only validated his work, but also inspired a new generation of physicists to explore the universe in ways that were previously unimaginable. The impact of this era continues to resonate in the scientific community, influencing countless discoveries and innovations. Today, the legacy of general relativity is evident in many aspects of our daily lives. From GPS technology, which relies on precise calculations of time and space, to the study of black holes and the expansion of the universe, Einstein's theories remain fundamental. General relativity has opened the door to new fields of research and has provided a framework for understanding the most extreme conditions in the cosmos. Its enduring legacy is a testament to the power of human curiosity and ingenuity. Even now, over a century later, the quest to understand the universe continues. Scientists are exploring the frontiers of physics, from the mysteries of dark matter and dark energy to the unification of general relativity with quantum mechanics. Each discovery brings us closer to a more complete understanding of the cosmos. The journey that began with Einstein's groundbreaking theories is far from over, and the quest for knowledge drives us forward, ever curious about the nature of reality itself.